Okay, let's go ahead and get started today. We're going to talk about a little more about arithmetic for computers, namely multiplication and division. Morden. So, I do want to step back and at least kind of admit that you probably have noticed that this course has been jumping around a bit. Fortunately, that's just the way it goes because there's a bit of a chicken and the egg problem with trying to understand how everything fits together. Wow, this must have been a great weekend. I need like 5 balls and go. Phew.
Just toss them at everybody.
Wow.
Everything okay?
Yes.
Okay, you're gonna be fine?
Yes.
Okay, good.
Sorry, I'm taking it back.
All right. So we're gonna step back. Hopefully you've seen the whole chain about, compiler translates into assembly. The assembler goes from assembly to machine code. We've looked about how we can have a processor translate those machine codes into actually something useful in our hardware. Maybe actually do additions or NANDs or load or move memory around inside the processor. And of course those circuits are based on gates, which we've talked about, AND gate, NOR gate, NOT. And then those gates are based upon transistors, and those transistors are based upon different type of doping. Good morning. So hopefully you at least see the whole chain here of computer architecture, and now we're going to kind of fill in a lot of the gaps that we have been missing.
Jonah.
Doing better, Jonah. Okay. So in case you didn't quite get addition, we're going to go over that real quick, and then we're going to cover integer multiplication and division, and then next class we're going to go talk about floating point. Yes?
Just found it funny because you're just like, in case you didn't get addition.
In case you didn't get addition, hey.
So, in case you don't get
Well,
basic
I
math,
mean, there's
here you
addition,
go.
right, and then there's subtraction.
It's really tricky business.
It's really tricky. It's just addition's tricky friend, right?
Yeah. You just add the negative.
Yeah. Whoa. Okay.
Whoa.
Whoa.
That's how you do it?
Again, if you have binary, let's see, you're adding 2 numbers. We still carry bits over. As you can see over here, we talked about that with actually a half adder and a full adder. Similarly to how you do in base 10, except for now it's base 2, so you have 0 and 1. Of course, 1 being high voltage and 0 being low voltage, or they like to put it negative voltage. Sure, whatever.
Whatever they say.
When they were doing subtraction, they would first make the negative. We talked about how this was done via 2's complement. And then they would actually add the 2 numbers. Since, you notice in this picture, the 1 comes down, and then afterwards there's this carry bit that zeroes everything out, and then there's an extra 1 on the other side. That overflow is ignored, which is why you get the answer 1 when you add -6 to 7. At least in our hardware, which is of course what you want it to do. Everyone good with this? Mm-hmm. All right. As a side note, some languages like C ignore overflow. So when there is overflow, we don't care. C doesn't care really about anything. Java's the same way. Some languages will actually require you to raise an exception. So if there's overflow, it stops your program and then tells you what happened. Maybe that's actually useful, but we found most of the time it's not. Just account for overflow and move on from there.
Don't make overflow.
Don't make overflow. We're going to go into this a little bit in more detail, but you've probably heard a lot about graphics. What happens is you may have, instead of having one instruction do one type of addition, you'll have an instruction do multiple additions. So maybe you have can use an instruction with a 64-bit adder to do 8-bit additions in parallel, or 416 or 232 vectors. Anyone remember why the 8 bits is important for graphics?
Because it likes it.
It likes, okay, that's true. Any other graphics design people? How many numbers can you represent with 8 bits?
A lot.
Oh, well.
Oh. More than 2.
More than 2, great. Come on, what's the exact number?
64.
Yeah, 256. Does that ring a bell with anyone when they're doing colors?
257?
Yeah, so you have red, green, blue, alpha. Each one of them can go from 0 to 255. So it requires 4 or 8 bits to do it. And then if you have 8 in total, you can actually do 2 parallel, basically pixel addition or subtraction, depending on what you're trying to do. In parallel.
Isn't it actually technically 257 numbers because you could have 0?
It's actually 0 to 255. But good catch. Oh.
Thanks for playing.
We talked about 2's complement. There's also something called clipping in audio, but we'll actually go into more of this later. Just wanted to at least give you an idea that, hey, look, what's coming down the pipe is doing more additions or more multiplications at the same time. Okay, hey, let's do multiplication. Hopefully this is the way you were taught multiplication. I don't know. Oh, wait, no one's done Common Core, right?
No.
Okay, great. So you're actually...
That's after us. Good luck when those students
Yeah, I'm actually kind of scared. I don't know what I'm about ready to have. Maybe it's a good thing.
They teach like everything differently now.
Yeah, they don't.
No, we learned it.
So
It's really dumb.
yeah, I have to apologize to my daughter all the time. So 1,000 multiplied by 1,001. Of course, these are in binary. So hopefully y'all remember how you do multiplication. You just multiply by the first digit, put it here, shift over, multiply again, and you add them all up.
Whoa.
Everyone remember that? Good
Yes.
refresher? All right, so our first multiplication hardware is going to look very similar to this. If you look on the right, we're going to, let's see, store the multiplicand up here and the multiplier over there, and then we're going to simply send it to the ALU and do the additions. So this is really the first bit of all we're going to do today, because we're just going to do this for multiplication, find a faster way to do it, and then do division and find a faster way to do it as well.
And that's it?
Yes.
That's all we're learning today?
Yeah.
Basic math. Binary.
Short day?
Hmm?
Tried to show it in a diagram. It's gonna
I have a feeling it's not going to be a short day.
No.
No.
But it's just
That
gonna
was
take a
good.
while to
That was good.
explain.
So let me go ahead and Lisa write up, because you're going to be doing this for your homework.
No, great.
Yay.
Let's see, we have 4 bits, so we're going to do 4-bit multiplication. So let's go ahead and start our little chart. We'll start with the, what are we going to do? What do we got? The multiplicand. Multiplicand.
And then
what's-
multiplier.
And then the multiple.
It's a D, not a T at the end.
Multiplier. Thanks.
You're welcome.
Step 0. So the multiplicand, which one's that? We're going to, 1,000. Multiplier will start at, was it 101? Sure, 1001. And then, of course, we have the product. Okay. All right. So let me go ahead and jump over to the people watching online who can't see that.
Don't we not have online students?
No, but
Yeah,
we
we-
have us.
We have us.
I mean, I could just not record this.
No,
so-
No, it's fine. I was just.
Trust me,
Well, I
it
was-
helps.
Hi, future us.
Okay. Hi, future us. All right. So what does the product start with? Just looking at the board. At the beginning, the product is
1,000.
0,
Jigger.
because you got to start it all at 0. And how many bits is the product going to be?
4.
No.
3.
8. Why is it 8 bits?
It's 4 and 4.
4.
Yeah, because that can multiply up to 8 bits. So you got to do 8 bits here. Notice I decided to do 4 bits times 4 bits and not 32 times 32. I would just, well, I'm already tired. I'd be even more tired after that.
Yeah.
All right, so step 0. What do? We look at the multiplier. We test if the last bit is 1. Is it 1?
Yeah.
Yes.
Yes. Okay, so we're going to add what to the product?
Huh? 1,000.
Which is the
The
multiplicand.
1,000?
Right, so we're going to add 1,000.
I think you got a lot slower. What did it do?
All right. So then that comes out to 0, 0, 0, 1, 0, 0, 0.
You
Great.
missed a 0.
Yeah. Thank you guys.
Yep.
I'm really tired today, so thank you. Then what do?
Have you had your tea yet?
Next step.
No.
You need your tea.
I do need my tea. Well, hold on. We gotta do something with the multiplier. Let's jump back and see what we do with the multiplier, because we're not done.
Oh.
The multiplier gets what?
Shifted.
Shifted to the
Right.
Left.
right. Multiplier shifted to the right.
So it goes down
So
100?
that 1 is gone. So we go 0, whoops. 0, 1, 0, 0. All right. What happens to the multiplicand?
It's
Shift to the left.
Shift to the left.
Yeah.
What does that imply that how many bits are in the multiplicand?
5.
Well, in
Wow.
total, it's going to be 8.
Eight.
So we need to add some zeros up there.
Can we just do this the other way?
What other way?
That way that makes more sense.
The way that was on
This
the
is how the computer
slides.
does it.
Oh.
No, the way on the slides was just a refresher in case someone forgot how to do multiplication. Hey, it could happen. All right, so this gets shifted to the left, so we get 0, 0,
Right, forget to have the new basic
0,
addition.
1, 0, 0, 0, 0. All right. Woo. Well, that was step 0.
Step 1.
Down to step 1.
Oh, wow.
What?
So much fun.
Now, well, what do we do again? We test the last bit of the multiplier. It's 0, so we don't do anything. Well, we don't
just
do
shift.
anything to the
We
product.
shift
We shift. What do we shift?
the multiplier and the
Alright, so
multiplication.
Right. So we do shift those. So let me go ahead and write. We don't do anything to the product. That's good. We're going to shift the multiplier to the right, and we shift the multiplicand to the.
Left.
0, 0, 1, 0, 0, 0, 0.
All right.
I get something because it's easy.
What was that?
I said I finally get something because it's easy.
Oh. All right. Now what do we do?
That's the exact same.
Test the
it
last
again.
bit. Is it
And
1?
It's 0, so
It's
do it again.
0, so we're going to move it all down. Which way does the multiplier go?
Right.
It's gonna be 1 next time.
Whoa. And this guy goes which way?
Left.
Oh no, the ones.
All right. So on to step 3. By the way, how are we doing back there? Doing good? Excellent. All right. Is it 1?
Yep.
Yes.
Yep. So what do we do?
Add the nothing.
It's 1, so we're adding what to the product?
No.
The multiplicand, right?
Can do.
Which equals, what is it, 0, 1, 0, 0. All right, and what do we do to the multiplier?
Shift right.
Shift to the right. Oh, hey, look, it's all zeros now. What do we do to the multiplicand?
Shift to the left.
And we actually stop. And the reason we stop is we've executed 4 times, and it's a 4-bit number.
Ah.
Hmm.
So you actually,
That P.
so with multiply, that's gonna be a little different with
Yeah.
division, but with multiply, you execute the same number of times as the bitness.
The
Bitness.
The bitness. All right. Okay. Any questions about that on the right?
Care of business.
The what?
I'm just saying to her, I was like, taking care of business.
Every day. Okay. All right. What issues do you see with this multiplier?
Takes a while.
It takes a while.
That's annoying.
All right. Yes, it does take a while. It's annoying.
She said it takes a while. I said it's annoying.
Well, what does the computer care how annoying it is?
No.
No, it just does it.
It doesn't have feelers. All right.
Yet.
Yet. Well, not according to Elizabeth.
Well, like you said, if you did 64 by 64.
That's a whole nother problem.
Oh my gosh.
Forever. Do it by hand.
To do it, okay, sure, to do it by hand, but the computer doesn't care. It's the computer, right?
Yeah.
Look up here. In this example on the board, we're trying to multiply two 32-bit numbers.
Ugh. Ugh.
What's the only thing that actually needs to be 64 bits?
Product.
The product.
Why is it alien?
But yet we have a 64-bit ALU, which makes, well, it makes sense because we got the multiplicand can be up to 64 bits
yeah.
and the product 64. So obviously you're going to need a 64-bit ALU.
Yeah.
The multiple can is also 64 bits. So, do y'all see that there's kind of a wasted space? Hopefully you see with our, if we did our ripple carry adder or even our carry look ahead, making the ALU 64 bits wide adds a lot of hardware and actually slows down the system as well because you got to do a lot of gates in parallel. So it'd be nice if we could at least eliminate or trim down the bitness of the ALU and the multiple can.
So you're taking care of
Anyone have any ideas?
Could break the number in half maybe or something like that, like do it separate and then add it afterwards or
That's a
something?
great idea. So this product, we're really operating, we only need to operate on half of this and then we're shifting it. Y'all see how we're kind of shifting the multi-can up? We can do the same thing with the product. I think the picture will really drive it home. All right, or we'll have that picture first. Okay.
JK.
So here's a different example. Notice now the multiple can is going to stay 32 bits. The ALU is 32. We're only going to operate on the top half of the product, and then we're just going to shift it all down, because that's really what we're doing with the multiplier. It's kind of got to think about what we're doing with the multiple can. You're shifting it up in order to add to the right part of the product. Well, that's similar as if you put in the product and you kind of shifted it down instead. Okay. So to send this home, we should do this on the board. Everyone good with that?
Yeah.
All right. So
Yay, drawing.
all right. So let's go ahead and start this off. All right. Give me two. You want to stick with 4-bit numbers?
Yeah.
Yeah.
Yeah, I bet you do. Okay, I bet you do. All right. Let's. What do we have? We only have the multi-can, and we don't even have a multiplier anymore. Whoop. Yeah, that's right.
Who needs a multiplier?
Yeah, notice we got rid of a whole register, which is pretty good. Yeah. All right, give me 2 4-bit numbers.
1101.
1101, and the other one.
0011.
All right, so this time we're going to put the 0 first, and then 0011. Is that what you said? Okay. Great. Who wants to do this one?
Will I
Wow.
Son of a bus.
No one? No volunteers? What am I going to do? Oh, don't make me call on Jonah.
Yeah,
Don't call me, because I have no idea.
He hasn't done this yet. He hasn't been up at the board. I think he needs to take the gauntlet.
No, I mean,
Shut up, David.
we're all going to help you, okay, Jonah?
Alright.
So, excuse me, guys.
Thank you, David.
Rite of passage.
Here I go.
Jonas always going.
Did you get a haircut?
To all the
I
people
did.
watching online. they're
Hello,
viewers.
future us.
Alright, what am I doing?
You're multiplying 2 numbers. You remember how to do that?
Yes.
Good.
What 2 numbers am I multiplying?
All right, multiply the multi-can and the product.
Okay.
So what's the first thing you test?
If it's a 1.
In the
Multiplicating, right?
other
In the
one.
product.
In the product.
Okay. And it is, so then I just write that down, right?
All right, so there's a 1 in the product.
Yeah.
We're trying.
So that means we need to add something to something. What are we adding?
The
We add
multiple can.
this to that.
No.
Yes, but which part of that?
The last part.
The last part. You pointed to the front part and then to the last
Oh,
part.
well.
He's not pointing.
first
I'm just, yeah, I don't know if I'm pointing.
The
I'm
first
just-
part.
Yeah, this part.
The first part.
No, it's the first
The
part.
first part.
Yeah, this part. That's what I said. So, alright.
Great. Okay, so do it.
So
So,
add it?
alright. So, this is still the
That
first
stays
step,
the same.
right?
We never- yeah, step
Okay.
0. We
So
don't
then-
start at 1.
Who starts at 1 anymore?
And then this stays the same.
Okay. Now what do we do?
Then we have to shift this.
Right.
right?
Uh-huh.
And we shift it to the right.
Yes.
Okay.
We're gonna find out soon if we did this in the reverse order. That's okay.
Uh-oh.
Yep.
Did I do it in reverse order?
We'll see in a second.
We'll find out.
All right.
We'll find out.
So then, I guess, hold on, let me keep going down, right? So then this shifts to the right,
Uh-huh.
so it'd be 0, 1, 1,
Move your head to the left or the right.
Zero.
Yeah, there we go.
1,
Zero,
0, 0, 1.
All right. Yes.
This stays the same.
It's gonna be shifted.
Or no, it shifts to the left.
Eventually.
Yeah.
Yeah.
No, it doesn't move.
So this doesn't move.
No, it doesn't move.
Y'all is steering me wrong. Look at that.
I'm good.
Well, because we shift the multiplier to the right.
Now you go to
Now
step
the
1.
product is the product.
Alright, so now,
Gotcha.
we gotta
We
step-
need better markers.
Yeah, this one.
Where's
is-
the black marker?
Here, there's another marker up there, Jonah. So just take that, throw it over here.
Where?
In the garbage can.
Which one should I use?
Aww.
No basketball for you.
It's fine. I knew that. Alright. Okay, this is better.
Now rewrite that 1 real quick. It looks like a, I don't know what, I think a hangman.
Sorry, there's a glare right there for me.
We're good. All right.
Draw a box and say Blair.
No.
Why not?
Alright, so then, so then do the same thing, right? Check and see if it's a 1.
Yep,
It's a
it's a
1.
one.
So, multiply it by this. Then you add that again.
Mm-hmm.
Okay. So then this would be, and then,
Wait, does the multiplier not get shifted?
Yeah, it never gets, the multiplicand never gets shifted.
Okay.
so then,
Now there is an overflow, so you.
Yeah, so then you'd have to-
allow that overflow. Your product is technically 1 bit higher, so it's 17 bits in a minute.
so it'd be 1, 1, 0, 0, and then the 1 would be over here, right?
Yeah, which is fine. Go ahead and write that 1.
Go ahead and write it?
Yeah. And then write the rest of your product. All right.
Which, well,
And
This
then
is
what
the
else do you
same.
need to do to your product?
and then shift this to the right.
Yep. So now you don't write that. You don't have to write that leading 0 anymore.
Okay.
Well, the reason for putting that 1 is it actually does go in that final product. So make
Oh,
sure.
so put this over here?
Yes.
Oh, okay.
But that, yeah, you got it.
1, and then
1, 1, 0.
1, 1, 0, 0.
Okay.
And this stays the same. And step 2, right?
Yep, step 2.
Look at us. Moving.
Oh.
It'll be a little easier now.
Yeah, because it's 0. So then you just keep it the same, right?
Well, when
Well,
do-
you keep it the same and then shift it.
You gotta shift it, yeah.
So that'd be 0, 1, 0, 0, 1, 1, 0, right?
Mm-hmm.
And then this stays the same.
Step 3.
3.
See, I'm not the only one who writes my 3s that way.
Well, I mean, it's on the board. And then this is just the same thing, just shifted.
Yep.
0, 0, 1.
All right, now what do we do? Don't tell them quick.
Wait, yeah, you guys
No,
did
we're
do
at
it
the,
one
we,
time.
we don't have to do it
So-
again,
Wait,
right?
No, why do we
Wait.
keep
We're at the
that
end.
1?
Wait.
You have to do it one more
Yeah,
time.
it's
Yeah.
Oh wait, no, that's
isn't
the
it
I had
that's
to do-
done.
that was the
That's
fourth
fourth
one.
step.
So it's
You've
done.
done 4 steps, right?
Yeah.
You've done 4 steps. The business is 4. You're done. Write
Yeah.
the word stop.
All right.
Yay.
It's a little angled, but that's
Okay. Now let's go see if it actually, are we actually correct?
Oh, here we go.
Because what are we multiplying? 3 times, what's that, 8, 12, 13, which is what, 39?
Here, I get up.
See if we did that right.
I'm gonna go sit down.
Sit down there. So yeah, it's what, 8, 12, 13 times 3, so we should get 39. So we have, let's see, what do we got? So that's 8, 16, 32. So we have 32 plus 4 plus 2 plus 1, 6, 8, 9. Good job, Jonah.
Woo!
All right. Hopefully you can see that if the bitness is a lot higher, like in your homework, you're going to have to write a lot more digits. But this is how you need to write your homework out. Okay?
Okay.
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 You said we got 3 homework out this semester.
Thanks, Carla. You got that from Matt, didn't you? All right.
Well, we're on the second one.
So again, recap. Why is this multiplier superior to the previous one?
Because you
It
knocked out a whole thing.
What did it knock out?
takes less space.
You have one less register, correct. Got rid of a register. What else did we get rid of? Or what else helped, I should
The
say?
multiplicand's half the size.
Multiplicand's half the size, so it's like getting rid of a register.
And the ALUs have the size.
And ALU's half the size, which is actually the biggest benefit, because that means your addition is going to happen a lot faster, probably about twice as fast. All right. Can anyone think of how we can improve the performance even more? And I'll give you a hint. Don't think about this anymore. Just think about a different way to do it. Let's say you have as much area as you want to do. You have as much area as you want. What can we do instead? Let's say area is not a concern.
Whole
It's
bunch
all
of
about
adders.
a whole bunch of adders. Why would we have a whole bunch of adders?
Just adding simple.
Okay. No, you got it.
Ah.
Okay.
So let's just put a bunch of adders a
I'm
row.
laughing because he just kind of like looked at me like, all right.
I'm tired.
I know.
All right, let's look at
Do
this.
your teeth.
So we're just gonna do all the additions in parallel. We're gonna put a bunch of, well, up here we have 32. Well, we have 32 adders, but actually on the first row, how many do we have? I think we have 32 32-bit adders.
Oh my gosh.
Yeah. And then
This is a big
it goes
machine.
down by 1 each time. What's that?
So this is a big machine.
It's a pretty big machine until you finally do our final 32-bit adder at the bottom. So you just send it and it just goes straight through. We don't have registers because we're just sending them right from one ALU to another all the way down the line until we get to the final answer at the end. I'm not going to test you over this, but we want to talk about this. So what's the advantage here?
This speed.
It's speed. There's a huge speed advantage. What's the disadvantage?
Space.
Space. Space.
Space.
Space. So here's
Final
frontier.
can be pipelined. We haven't talked about pipeline. Remember I was telling parallelism, prediction, and pipelining are the 3 P's of improving performance. I mentioned at the beginning, I haven't been going over it much, but we're going to start really getting into it. This one is pipelining. Any idea what pipelining is?
Isn't it just directly forwarding it from one process to another process, so you don't have to do any interpretation? I mean,
You're going along the right path.
The laundry room
Design.
example.
Yeah, the laundry room example.
Yeah, you put your clothes in the wash, and then you put your other clothes in the dryer, so you can have both going at the same time.
Yeah, so there's parallelism there. They're not happening fully in parallel, but you can start the next instruction right behind the current one.
Yeah.
So if you look at it, once this kicks off and is to the next level, you can start the next one, right? Because they're all just going to flow. So in actuality, you can, with 32 bits, you can have 32 multiplications going on in parallel through this machine if you pipeline it correctly. Yeah.
Fast.
So there's a lot of optimizations, or at least performance here. By the way, there are a ton of other multipliers out there. This one usually is not used because that is a lot of additions that you've got to put on your processor, and that would take up a lot of area. And there turns out to be other multipliers that are more efficient for the general case, because in general, some of your bits are going to be 0, right? So you're doing a lot of additions unnecessarily with this pipelining. But it does have a cost-performance trade-off, and we're only going to study those first 2 for now, and at least talk about the fact that we've come up with faster multipliers. All right, any questions? Because you will see what we did on the board in your homework and in a midterm.
Which will be
We're not
Apparently
too
after
soon.
spring break. What's that?
Too soon.
Too soon. Okay. Let's
So
go.
it is going to be after.
You want it after or before? Quick.
After.
All right, there we go.
Alright, there we go.
Just
Yay.
keep it, well, the reason I ask is if we do it after, you may not have your midterm grade back before withdrawal period. But y'all, none of y'all are going to withdraw, I assume.
No. We don't have a choice.
Yeah, that's the other problem, right? You have much of a choice here.